Environment and intelligence research investigates the impact of environment on intelligence. This is one of the most important factors in understanding human group differences in IQ test scores and other measures of cognitive ability. It is estimated that genes contribute about 20 to 40% of the variance in intelligence in childhood and about 80% in old age. Thus, the environment and its interaction with genes account for a high proportion of the variation in intelligence seen in groups of young children, and for a small proportion of the variation observed in groups of mature adults. Historically, there has been great interest in the field of intelligence research to determine environmental influences on the development of cognitive functioning, in particular, fluid intelligence, as defined by its stabilization at 16 years of age. Despite the fact that intelligence stabilizes in early adulthood, it is thought that genetic factors come to play more of a role in our intelligence during middle and old age, and that the importance of the environment dissipates. Neurological theory. As babies, our neuronal connections are completely undifferentiated. Neurons make connections with neighboring neurons, and these become more complex and more idiosyncratic as the child ages, up until the age of 16, when this process halts. This is also the time frame for development of what is defined in psychometric studies as the general factor of intelligence, or G, as measured by IQ tests. A person's IQ is supposed to be relatively stable after they have reached maturity. It is likely that the growth in neuronal connections is largely due to an interaction with the environment, as there is not even enough genetic material to code for all the possible neural connections. Even if there was enough genetic material to code neural connections, it is unlikely that they could produce such fine-tuned connections. In contrast, the environment causes meaningful processing as the neurons adapt to stimuli presented. The capacity of the brain to adapt its connections to environmental stimuli diminishes over time, and therefore it would follow that there is a critical period for intellectual development as well, while the critical period for the visual cortex ends in early childhood. Other cortical areas and abilities have a critical period that lasts up through maturity, the same time frame for the development of fluid intelligence. In order for a person to develop certain intellectual abilities, they need to be provided with the appropriate environmental stimuli during childhood, before the critical period for adapting the neuronal connections ends. The existence of a critical period of language development is well established. A case illustrating this critical period is that V.M., a young man who was born profoundly deaf and did not have any interaction with the deaf community. At the age of 15 he was fitted with hearing aids and taught Spanish. However, after 4 years he still had severe difficulties in verbal comprehension and production. Some researchers believe that the critical period effect is a result of the manner by which intellectual abilities are acquired, that changes in neuronal connections inhibit or prevent possible future changes. However, the critical period is observed at approximately the same age in all people, no matter what level of intellectual ability is achieved. Environmental influences. Sociocultural. Family. Having access to resources of the home, and having a home life conducive to learning is definitely associated with scores on intelligence tests. However, it is difficult to disentangle possible genetic factors from a parent's attitude to use of language. For example, a child's ordinal position in the family has also been shown to affect intelligence. A number of studies have indicated that as birth order increases, IQ decreases, with firstborns having especially superior intelligence. Many explanations for this have been proposed, but the most widely accepted idea is that firstborns receive more attention and resources from parents and are expected to focus on task achievement, whereas later borns are more focused on sociability. The type and amount of praise received from family can also affect how intelligence develops. Research by Dweck and colleagues suggests that feedback to a child on their academic achievements can alter the future intelligence scores. Telling a child that they are intelligent and praising them for this intrinsic quality indicates that intelligence is fixed, known as entity theory. Children holding the entity theory of ability have been reported as performing less well after a failure, perhaps because they believe that failure on a task indicates that they are not intelligent, and that therefore there is no point in trying to challenge themselves after failure. Dweck contrasts this with incremental theory beliefs, the idea that intelligence can be improved upon with effort. Children who hold this theory are more likely to develop a love for learning rather than for achievement. Parents who praise the child's effort at a task rather than the result are more likely to instill this incremental theory of intelligence in their children and thus to improve their intelligence. Peer group. Junior Harris suggested in The Nurture a assumption that an individual's peer group influences their intelligence greatly over time, and that different peer group characteristics may be responsible for the black-white IQ gap. Several longitudinal studies support the conjecture that peer groups significantly affect scholastic achievement, but relatively few studies have examined the effect on tests of cognitive ability. There is some evidence that peer groups influence tests of cognitive ability. However, the peer group an individual identifies with can also influence intelligence through the stereotypes associated with that group. The stereotype threat, first introduced by Claude Steele, is the idea that people belonging to a stereotyped group may perform poorly in a situation where the stereotype is relevant. This has been shown to be a factor in differences in intelligence test scores between different ethnic groups, men and women, people of low and high social status, and young and old participants. For example, females who were told that women are worse at chess than men performed worse in a game of chess than females who were not told this. Education. IQ and educational attainment are strongly correlated. There is controversy, however, as to whether education affects intelligence. It may be both a dependent and independent variable with regard to IQ. A study by Ceci illustrates the numerous ways in which education can affect intelligence. It was found that IQ decreases during summer breaks from schooling. Children with delayed school entry have lower IQs. Those who drop out of education earlier have lower IQs, and children of the same age but of 1 year's less schooling have lower IQ scores. Thus, it is difficult to unravel the interconnected relationship of IQ and education where both seem to affect one another. Those who do better on childhood intelligence tests tend to have a low dropout rate, and complete more years of school and are predictive of school success. For instance, one of the largest ever studies found a correlation of 0.81 between the general intelligence G factor and GCSE results. On the other hand, education has been shown to improve performance on intelligence tests. Research controlling for childhood IQ and treating years of education as a causal variable suggests that education causes an increase in total IQ score, although general intelligence was not affected. For instance, a natural experiment in Norway where the school-leaving age was changed suggested that IQ was raised by additional year of school. School may alter specific knowledge, rather than general ability or biological speed. In terms of what matters about school, it appears that simple quantity or years in school may be what underpins the linkage of education with performance on IQ tests. Training and interventions. Research on the effectiveness of interventions, and the degree to which fluid intelligence can be increased, especially after age 16, is somewhat controversial. Fluid intelligence is typically thought of as something more innate and defined as immutable after maturity. One recent article, however, demonstrates that, at least for a period of time, fluid intelligence can be increased through training in increasing an adult's working memory capacity. Working memory capacity is defined as the ability to remember something temporarily, like remembering a phone number just long enough to dial it. In an experiment, groups of adults were first assessed using standard tests for fluid intelligence. Then they trained groups for 4 different numbers of days, for half an hour each day, using and back exercise that worked on improving one's working memory. It supposedly does so through a few different components, involving having to ignore irrelevant items, manage tasks simultaneously, and monitor performance on exercise, while connecting related items. After this training, the groups were tested again, and those with training showed significant increases in performance on the fluid intelligence tests. A study by Blackwell et al. Found that they could improve a child's mathematics achievement depending on which theory of intelligence they were taught: incremental or entity theory. Entity theory supposes that intelligence is fixed and cannot be altered by working harder. Incremental theory, on the other hand, assumes that intelligence is malleable and can be developed and improved with effort. Over the course of a year, they found that students who had been taught the incremental theory of intelligence showed an upward trajectory in grades in mathematics throughout the year, whereas those who had been taught entity theory showed no improvement. This indicates that teaching incremental theory may improve performance on academic tasks, though further research is needed to investigate whether the same results can be found for general intelligence. Other studies have looked at improving intelligence and preventing cognitive decline by using cognition-enhancing substances known as nootropics. One such study gave participants a number of nootropics in combination in the hopes of targeting numerous cellular mechanisms and increasing the effects on cognition that each would have if administered individually. They conducted a double-blind test and administered the combination treatment, a placebo, to adults for 28 days. They administered Raven's advanced progressive matrices as a measure of intelligence on the first day and after 28 days. The results indicated a significant improvement in performance for those who had taken the treatment compared to those taking the placebo. The effect was equivalent to an increase in IQ of around 6 points. Environmental enrichment. Environmental enrichment affects cognition and intellectual development from a neurobiological perspective. More stimulating environments can increase the number of synapses in the brain, which increases synaptic activity. In humans, this is most likely to occur during the development of the brain, but can also occur in adults. Most of the research on environmental enrichment has been carried out on non-human animals. In an experiment, 4 different habitats were set up to test how environmental enrichment or relative impoverishment affected rats' performance on various measures of intelligent behavior. First, rats were isolated, each to its own cage. In a second condition, the rats were still in isolation, but this time they had some toy or enriching object in the cage with them. The third condition placed the rats in cages with each other, so they were receiving social enrichment without any enriching object. The fourth and final condition exposed the rats to both social interaction and some form of object enrichment. In measuring intellectual capacity, the rats who had both forms of enrichment performed best, the ones with social enrichment performed second best, and the ones with a toy in their cage performed still better than the rats with no toy or other rats. When the volume of the rats' cortices was measured, the amount of enrichment again correlated with larger volume, which is an indicator of more synaptic connections. and greater intelligence. Attaining this sort of information in humans would be difficult as it requires histological research. However, studies where environmental deprivation has occurred provide insight and indicate that a lack of stimulation can lead to cognitive impairment. Further research using educational attainment as an indicator of cognitive stimulation have found that those with higher levels of education show less signs of cognitive aging, and that stimulating environments could be used in the treatment of cognitive aging dysfunctions such as dementia.